All right, Mavericks and Wizards and Trailblazers. In this virtual lesson, we are going to talk about two really big ideas that constantly show up on the AP exam: area between curves and volumes of revolution. What I'm going to do before we actually launch into any of the AP problems is talk through sort of the big ideas, make sure that we have a common understanding of how we go about doing this, how the integral is going to assist us in doing this, and then we'll actually look at two of the AP problems that have been used in previous years and work through it step by step. I hope this winds up being a good experience for you and for me and for everybody else. So here we go. So let's go back in time for a few minutes and think about how we first were introduced to area. In AP Calculus, we would have started the conversation by looking at a curve. In this case, we have some curve, f of x. Maybe you think it's parabolic, maybe it's part of a sine function. That's not so much what matters right now. What we're interested in is approximating the area underneath this curve, which is above the x-axis, between A and B. We would have had conversations about taking this interval A to B, dividing it into intervals, looking at the rectangles, or in some cases the trapezoids that are generated. By finding the area of each of these rectangles and adding each of these rectangles up, we get an approximation for the area. In this case, I believe this is a diagram where we're using the right endpoint method. If you look closely, you can see that on each interval, it is the right endpoint that is being used to determine the height of the curve. So I would take that height times the length. That gives me the area for one rectangle. Add them all up. That gives me an approximation for the true area. But now the approximation in this case is going to have a mix of, on this side, an overestimate. I see the rectangles are extending above the curve. Over here it's an underestimate because I have some of this white area that's not being captured in the area. We're going to add all of those up to get an approximation. At the end of the story, what you can find though is that if you bring on infinitely many rectangles, you can move from these approximations to an exact area. And the exact area is found by integrating the function f of x with respect to x from your starting point to your ending point. And so the true area would be given by that expression. At this point in the AP Calculus course, this is something that I expect most students are very, very comfortable with. They see this, it automatically happens behind the scenes. On the AP exam, you need to make sure that you write the integral expression. From there, if you needed to determine an exact answer, you could use your graphing calculator. Lots of options available there. You could use properties of integrals. You could use your fundamental theorem of calculus. Lots of ways to go about getting this area. But we need to keep in mind, all throughout the rest of the problems, that the integral gives us an approximate, it gives us the exact area underneath the curve from a starting point to an ending point. We're going to work through some more complicated problems and we'll see how that goes. In this example now, instead of looking at the area bounded by one curve in the x-axis, we're going to look at the area bounded by two curves. So the conversations that we start having now, if I wanted to find the area of S, well, I can see that S is the region formed by this shape over here. We're going to call this f of x. F of x is the top function. By this curve over here, which is g of x. I can see that there's an intersection point over here. This is what I'm going to refer to as A. And an intersection point over here at B. If I want to find the area of S, but just S, well, let's go back to our idea of the integral. If I set up an integral expression that says we're going to integrate f of x, the top function, with respect to x, starting at A and going to B, then that means I have dropped a vertical line here going through x equals A. Here at x equals B. This area would represent the entire area from A to B, which is bounded above by f of x and bounded below by the x-axis. Unfortunately, all I want is the area of S. I don't want the white area. So in order to get rid of the white area, I'm going to subtract from this integral the area from A to B underneath the curve g of x with respect to x. This difference of integrals will take the entire area underneath f of x, subtract out this area that I don't want, leaving me the area of s, which was our desired area. With practice, some students are now at the point where they realize that instead of two integrals, since we have the same starting values, the same lower limits, the same upper limits, we can actually reduce this to one integration step. It'll be f of x minus g of x with respect to x. In my calculus class, we just talked about it being the top minus the bottom. Your top function minus the bottom function. That is a quick summary of how we find area. We will get to some more concrete examples, but this is what's going to be going on behind the scenes. Now we're going to look at a couple of demonstrations of how you take these regions that we know how to find the area of and turn them into three-dimensional objects, and how you go about finding the volume of those three-dimensional objects. All right, so we're going to look at a quick example here of a volume of revolution. We're going to start with this function. This function is the square root of the sine of x. So our upper function is f of x equals the square root of the sine of x. My goal is going to be to take this region over here, which is a light blue, and we're going to spin this. We're going to revolve it around the x-axis. Now, when we do that, we want to pay particular attention to what's happening for any little slice. For any particular x value, I want to pay attention to what happens here as we spin around the x-axis. If you have a good visual in front of you, or a good picture in your head, this line segment, as we spin it around the x-axis, is going to actually generate for us a circle. We're going to do that again. All right. So let's look at an example here. We have this function. The function that has been graphed is the function f of x equals the square root of the sine of x. And the instructions for this problem are going to be to take this region bounded by the square root of the sine of x, bounded by the function and the x-axis, and we're going to take this region and we're going to revolve it around the x-axis. Now, in order to do that, what we're going to do is, depending on your comfort level with the volume formula, you know that it is going to be pi times your function squared dx from our starting point to our ending point. Now, if you're not comfortable with that, let's take a moment and kind of explain where this is coming from. Where it's coming from is we want to stop and think about any particular x value. If I needed to find the height of the function at that point, I would evaluate the function at that point, which would generate x comma f of x and x and a y. I'm going to take this little line segment, I'm going to revolve it around the x-axis. Here we go. When we do that, you might not be able to see it so well on the videotape. As this little line is getting revolved around the x-axis, it actually traces out a circle. And it's showing up a little bit darker here. The way that we find the area for this particular circle is going to be, well, for any circle, we know that the area is determined by pi times your radius squared. The radius in this case is being determined by the y-coordinate. And the y-coordinate at this point is just f of x. And so we take our area, and it's going to be pi times the function squared. That's going to give me the area for this one circle. As we put all of these little thin circular slices together, what we're going to generate is actually the full three-dimensional object, which is this egg or this football. And so the area for a slice actually winds up, doing your integration from A to B, winds up giving you this volume formula, which we're going to use quite a bit. But this is sort of the behind-the-scenes what's going on. All right, so this is the last one that we are going to discuss before we launch into the formal AP problems. What I have up here on the board is a wireframe model for a three-dimensional object. And I want to tell you how this three-dimensional object was formed before we actually discuss the calculus involved in finding the volume. So this three-dimensional object has a base that is a circle, and I'll show you the circle in the xy plane. We started with the circle, and we made the three-dimensional object by constructing slices that run from one end of the circle across the other one. And those slices are actually going to represent squares. So whatever the distance might be from this point on the circle straight across is going to match the height of the square at that point. Since it's a square, we could find the area of any of these squares. Here come a few squares. By just finding the length of one side, we're going to multiply it by the height. That gives us the area for one square. Since this three-dimensional object is created by just lots and lots and lots of slices of squares, infinitely many squares, we can find the volume by finding the sum of all of these areas. Well, what is that? We know that the way we find the infinite sum is we're going to do an integration from whatever our starting point is to whatever the ending point is, and it's going to be the length of that square. We're going to take that length and we're going to square it with respect to x, and that's going to give us the volume for this three-dimensional solid. Now notice there's no pi in front of the integral. We had pi in front of the integral last time because the the object formed was a volume of revolution. All of the slices that we would take were cylinders, or it was a circle. Now we're looking at slices that are squares. The way we find the area of a square is length times width, side squared, any way you want to think about that. So that is the end of the big ideas. Now what I want to do is launch into two AP problems that have shown up on previous exams, and we're going to do a full work-through of the solutions. If you need more support on the ideas of area under a curve, area between two curves, volumes of revolution, or volumes with these known cross-sections, I would encourage you to find your AP Calculus Survival Guide and find the appropriate section. There are some problems to help guide your learning. Now let's look at the AP problems. All right, so here's the first problem that we're going to look at. We have region R, which is going to be in the first quadrant. The lower function is 2 times the square root of x. We have the horizontal line y equals 6 that makes up the other boundary. In part A, we're going to be asked to find the area of region R. We're going to approach this as the area bounded between two curves, or between two functions if you want to think about it that way. In part B, we're being asked to write, but to actually not evaluate, an integral expression that gives the volume if we take this solid and rotate it about the horizontal line y equals 7. We're going to work through that. And then lastly, we're going to be asked to look at the cross-section. We're going to be asked to find the volume of the solid formed by cross-sections. The cross-sections are going to be perpendicular to the y-axis. Those cross-sections are going to form rectangles where the height is 3 times the length of the base. We're going to completely work through the solutions to all 3 of those. So I would grab paper, I'd grab pencil, I'd grab your calculator, and let's just work through these problems and see what we can do. Okay, so let's get on this first problem. Same region that was defined before. I want to find the area. Of R. Well, in order to find that area, I'm going to be doing an integral. We're going to do top minus bottom. That's my favorite way to think about this. The top function is y equals 6. The bottom function, we've been told, is y equals 2 times the square root of x. If I'm going to find the area, it is going to be just top minus bottom, 6 minus 2 square roots of x. I'm going to integrate that with respect to x. Sometimes we do integration with respect to y. The last thing I need is I need my lower limit of integration. I need my upper limit of integration. Since the region R starts here on the y-axis, I know what my limit is going to be. I'm going to start at 0. My upper limit is determined by the intersection point of y equals 6 and 2 times the square root of x. In this example, you were actually given the intersection point, but I would also be prepared, if I were you, for finding that intersection point without my calculator. without it being given to me. The way that you would do that is if these two functions are equal, we're going to set the y coordinates equal to each other. We're going to solve it for x. We're going to divide both sides by 2. So we're going to get that 3 equals the square root of x. We're going to square both sides to get that x equals 9. That's your intersection point. That then becomes your upper limit of integration. If I'm going to integrate this function, and I believe this shows up in a no calculator section, what we're going to do is get it in in integration ready form, which is what I call it anyway. I'm going to rewrite 6 minus 2 square roots of x as 6 minus 2x to the 1/2. I'm integrating with respect to x. This should be a nice application of your general power rule for integration. The integral of a constant is just that constant times x minus 2. Instead of x to the 1/2, when I use the general power rule, you add 1 to the power, you divide by the new power. So this is going to be x to the 1/2 plus 1 divided by 1/2 plus 1. We're then going to evaluate that function from 0 to 9. Okay, let's clean that up a little bit. We have 6x minus, we have 2x 1/2 plus 1. That's going to make it to the 3/2 power. The denominator is also 3/2. If I'm dividing by 3/2, that's the same thing as multiplying by 2/3. So it's now going to be 6x minus 4/3 x to the 3/2 power. I still have to evaluate that function from 0 to 9. Fundamental theorem of calculus says we plug in the upper limit first. So we're going to have 6 times 9 minus 4/3 times 9 to the 3/2 power. From that, we're going to subtract the answer that we get by doing 6 times 0 minus 4/3, 0 to the 3/2 power. Depending on the expectations that have been set by your AP Calculus teacher, you've probably already been told that you can stop at this point. There is nothing left in here except for numbers. Numerical answers don't need to be simplified on the AP exam. This is a perfect answer. You can move on. If, however, it showed up on the multiple choice part of the exam, you need to be able to simplify it. So let's go through and do the simplification. 6 times 9 is going to be 54. Now we've got 4/3 times 9 to the 3/2 power. Back in Algebra 2 or whatever it was, you learned that the way you handle rational exponents, the denominator tells you what root to take. I take the square root of 9, which is 3. The numerator tells you what power to raise that answer to. So I took the square root of 9 to get 3. 3 cubed is going to be 27. From that, I'm going to subtract off all of this. 6 times 0 is 0. Minus 4/3 times 0 to the 3/2 is also 0. And I'm just going to finish this off. 54 minus 4/3 times 27. 27 divided by 3 is 9. Take that answer times 4 is 36. 54 minus 36 is 18. Feel free to high-five your neighbor. If you can make it to that point, you've just picked up 3 points on the AP exam. The first point was earned by setting up the integrand, which is the 6 minus 2 square roots of x, recognizing top minus bottom. The second point, I believe, was awarded by being able to integrate it correctly, getting to 6x minus 4/3 x to the 3/2, evaluated between 0 and 9. And the last point was for arriving at this numerical answer of 18, or any of the numerical steps prior to that, even if you didn't simplify it. Let's move on to Part B.